task 2. Now, best practice, before we start each of these separate tasks is to clear the contents of your workspace. So I don't know where your workspace panel is in your MATLAB desktop, but if you look at my screen, you'll see that my workspace panel is over on the right-hand side. We clearly have a whole bunch of the MATLAB variables that were produced during that task 1 script. So a really easy way just to clear the contents of that workspace is just to click on the Home tab sheet of the MATLAB desktop and then look for an icon called Clear Workspace. If you click on that Clear Workspace icon, it should delete all of those task 1 variables out of your workspace. So let's do that. That's a really good best practice. Alrighty. So on my computer, my workspace is nice and clean now, which is hopefully what you're doing as well. All right, so task 2. Apparently in task 2, we are now going to numerically solve those ODEs that we derive for this single degree of freedom concrete pipe pendulum. So just scroll down the script, and what do we got? So apparently this is where we finally define some numeric values for some of those system parameters. So you'll sort of see that we're specifying, for instance, the length of the pendulum arm. It's 0.25 meters. The pendulum mass apparently is 700 kilograms, etc. So unlike the previous task, what I'm going to get you to do here is let's just run the contents of this script in its entirety. Because ultimately what I want you to do is to start playing with the Simulink model that gets opened when we do that. So let's just click on the Live Editor tab sheet within your MATLAB desktop, and then come across to the biggest green triangle that you can see that should have the word Run underneath it. And then click on that Run icon, and it will run every section that is in your script from top to bottom. So please click on that Run triangle. Now I'm hoping that when you do that, this is the Simulink model, Simulink file, excuse me, that appears. So this Simulink file actually does 2 things. If I just sort of remind you of some of the really basic file navigation shortcut keys, if you open the Simulink file and it looked like you were staring at it from 10,000 feet above the ground, or alternatively, if the Simulink file opened and you've got your face pressed against the screen, neither of which are satisfactory, then the way to sort of make the file occupy the model occupy full screen is just to click anywhere in the white canvas of the Simulink file, and then hit the space bar key on your keyboard, and that should make everything fit nicely into full screen view. So there are this Simulink file that we've opened. It actually includes 2 implementations of this concrete pipe pendulum. The yellow implementation, which I'm referring to as the Brain-Newton implementation, and also the green implementation, which I'm calling the SimScape model. And whenever you've got 2 different ways of doing the same thing, it's always reassuring that when you compare those 2 different ways, that they produce the same answers. And that's what we're going to be doing in this example. So let's have a look at the Brain-Newton model, the yellow model first of all. So you should be able to sort of see some tab sheets embedded within your Simulink editor. So just click on the Brain-Newton model tab sheet, and that should take you inside the contents of this yellow subsystem block. So when I do that, again, once it appears, I'm just going to by default hit the space bar. And here is where we would have dragged that little yellow block that we produced in task 1. We'd paste it in and we'd wire it up. If this is the very first time that you've seen how Simulink can numerically solve ODEs, let me sort of give you the 30-second sort of summary. So Simulink is all about solving nonlinear dynamic systems. And one way that it can do that is if you define what an ordinary differential equation is, you can use Simulink's integrator blocks to then integrate those derivative terms. So here's how Simulink works. Say we've got this signal wire called theta double dot. Yep. We pass it through an integrator, and you know what happens when you integrate theta double dot? It's not a trick. What comes out of the integrator is theta dot. Yep. And if we take theta dot and we pass it through an integrator, you know what happens, right? Yeah, you get theta. So these sort of integrator blocks are at the very heart of how Simulink is able to numerically solve nonlinear ODEs. And yes, you're exactly right that it kind of looks like there's a feedback mechanism in the way that it does that, because if you follow the signal wires coming out of those integrators, you'll see that they're making their way back into the little yellow block. That's exactly what we need. So this is one way of getting Simulink to solve this system. In fact, look, at this point in time, I'd like to sort of just get you to click on that green run button, and let's immediately ask Simulink to solve this system of ODEs. Just click on that round green run button. When that happens, a little CAD viewer will pop up on your screen. Let's just forget about that for the moment, because that's in part 2 of our conversation. So I'm hoping that you've all been able to hit that green run button, and let's have a look at the results that have been produced. So let's double click on this pink oscilloscope block. The name of this oscilloscope block is called scope_Newton. So when you double click on that pink oscilloscope block, let's have a look at some of the time series results that have been produced. And here they are. So in all of these axes, time is on the horizontal axis. So you're looking at the time varying signal for theta double dot, the time varying signal for theta. The one at the bottom is clearly the time varying signal of theta. And then on the right hand side, you can see the 2 axes that show the time varying reaction forces Rx and Ry. So folks, congratulations. Just so that the significance of what we've done together hasn't passed you by, in task 1, we derived the ordinary differential equations for that concrete pipe pendulum. And we got the symbolic computing toolbox to automatically convert those equations into this yellow Simulink block. We've now asked Simulink to numerically solve those ODEs. And we're now staring at these time series plots that show that numerical solution of that system. Very nice. Well done. Well done. So if I now sort of climb back to the root of this Simulink file, which you can also do by clicking on this tab sheet. You'll see that in this Simulink file, not only did we include our brain-derived Newtonian model, but we've also included an alternate way of also modeling and representing the concrete pipe pendulum. And that alternate way of modeling is done using something called Simscape. So if you're kind of curious, you can click on this tab sheet, Simscape model, and by clicking on that tab sheet, it will take you inside the Simscape subsystem. Once you get in there, make sure you hit the space bar. So this is an alternate way of modeling that concrete pipe pendulum. All right. Just very, very quick. If I sort of double click on the pipe block, this is where we specify that this block represents the concrete pipe. Yeah. All right. So let me go back to the root level of the model again. So we've got our brain solution to solving the dynamics of this system. And we've also got the Simscape solution. And this is where I'm sort of going to come back to that CAD viewer that popped up onto the screen when we hit the green run button. So this CAD viewer, it actually pops up automatically whenever you have Simscape multi-body blocks within a Simulink file. So this CAD viewer appears because of this Simscape implementation. And the really nice thing about this CAD viewer is it's got lots of nice sort of interactive controls. Down at the bottom of the viewer, you can click on the playback controls that actually give you an animation of what this mechanical system is doing, which is just sort of swaying side to side. You can sort of click on some of the icons in the top of the screen, which hopefully are quite intuitive, and you can sort of change the viewing angles and so forth. So, all right, we've got the brain Newton model, we've got the Simscape model. I'm really hoping that these two different ways of modeling this produce similar simulation results. So let's click on the comparison tab sheet, compare. Let's click on this little guy. Once you get into that compare subsystem, hit your space bar. And inside this compare subsystem, you'll also see another one of those oscilloscopes. So let me sort of double click on this oscilloscope. When we do that, we get very, very similar looking time series plots that we had before. However, each of these axes now has two data sets plotted in them. So if I kind of just use my my magnifying glass to sort of zoom in, so let me click on that magnifying glass. And now I'm just going to sort of zoom in on just one of these. And after doing that a few times, you can see that we've got a yellow data set. That would be from our yellow Newton model. But we've also got simulation results in the way of these green dots, and that would be from our green Simscape model. So the sort of conclusion is that our Newton model is producing simulation results very, very similar to the Simscape model, which is quite reassuring. To bring the oscilloscope plots back to full view, this is the icon that you want to click on. Alrighty. So I think we're done. We're finished with task 2. So task 2 was simply about numerically solving the ordinary differential equations that we had derived in task 1. And it was also about sort of giving you some validation that the response of the Newton-derived model, its response was very, very similar to an alternate way of modeling the exact same system using something called Simscape. So I think we're done. I think we're done with task 2. So we can sort of close this guy. Folks, the remaining two scripts that are in this folder, they're called task 3 and task 4. Let's just open one of them. Let's say task 3.